Hi, my name is Francesca Barsamian, and I'm just presenting you with a video about calculus. I'm an academic tutor, and I tend to tutor high school and college age students in a variety of topics. Calculus is one of them. And I'd like to just show you a few different problems today from a typical calculus course. It's from the Stewart book. With the first problem, it's just integration of a pretty simple derivative here, 1 plus 3y minus y squared. And this is relating to the fundamental theorem of calculus, which is stating how while this is the derivative of f of x, if you take the integral of that, then you'll come up with capital F of x, which is the original function. So I'm going to integrate it here to get that original function, and I'm going to use these two limits of integration, 4 and 0, once I have the antiderivative. So the first step is to raise each power of each degree by 1 and to make it look like the original function. So the first step to do that would be to write 1x, because if the original function was 1x, then the derivative of 1x would be 1. So you're doing the antithesis of what you did before. In order to get the derivative of 1x, you would have written 1 in calculus 1, but now for calculus 2, you would be trying to do the opposite of that process to get the antiderivative. So 1x would be the opposite of that. In the next step, or sorry, I should have written 1y because it's actually written in terms of y. For the next step, I'm going to raise the power of y by 1. So before it was y to the first power, now it's y squared. Then I'm going to write a coefficient of 3 over 2, because in order to do the opposite of this process and get the derivative of 3/2 y squared, it would be 3y to the 1 power. So I'm taking 2 times 3/2 and getting 3y to the 1 to do the opposite of the integration process. For the third part of it, I'm going to raise the degree again by 1. So now I have y to the third. And then I'm going to write a coefficient of 1/3, because 3 times 1/3 is 1, which was the coefficient of the derivative here. So this would be the antiderivative of this original integral. Then I write a vertical bar, and I write the limits of integration, which are 4 and 0. Now I plug in 4 into this integral here. This was the first part from plugging in the 4. Now I have 4 plus 3/2, 4 squared, minus 1/3, 4 to the third power. Then I subtract the second limit, which is 0. So I'm going to plug in 0 and 0 and 0. And so I could actually just take a shortcut and write 0 there, because it's pointless to write out the complete integral again, plugging in 0, because it will simply equal 0. So from here, I could just solve all of this. I'll probably get a fraction for it, and that would be the answer. So this is something that you could do longhand or on your calculator. And this whole process is to take the curve, which is this here. This would be your f of y, and you're getting the area under the curve from 0 to 4, the 0 being A and 4 being B. And that's the entire point of taking the integral of the curve. You're getting the area from point A to point B, and it's the opposite of taking the derivative. Before, you were taking the derivative to get the tangent line to the curve. Now you have the tangent line, and you have the curve that represents all of those tangent lines, and you're trying to get the area under that curve. In the next problem I'm going to present to you, it's substitution from Calculus 2 once again. You're trying to simplify the entire integration process by setting u equal to some portion of the integral, and then you take the derivative of u, which would be u prime, and then you try to make it look like the original integral. So I'm going to take u equals this bottom portion, and it will actually look like this portion then if I do that. So I'm going to set u equal to 1 plus x plus 2x squared. So I have this u now. Du dx would then equal the derivative of this. So that would just be 1 plus 4x. Now I want it to look like this entire portion here, so I'm going to multiply dx to the other side. Now this looks exactly like this top portion, 1 plus 4x dx, which is exactly what I wanted. I'll rewrite the integral without any limits. It'll be an indefinite integral in the end. So I have u on the bottom with a square root sign because this was our original u, so I'm going to put it under the root sign, while this entire portion here was du. So this is my, my final integral, 1 over root u with no limits, and then du, because this entire portion equaled du. I could rewrite that in terms of a power, u to the 1/2, negative, and du once again. So u negative 1/2 du. Now I can take the antiderivative of that because it's completely prepared for that process now. U to the 1/2, and then if I write a 2 in front of that, this would be the antiderivative of u to the negative 1/2. Negative 1/2, okay, if I have this original antiderivative, 1/2 times 2 would be the coefficient of 1 here. So I've gotten the coefficients taken care of then. And then I would reduce this power by 1, which would equal negative 1/2. So 2u 1/2 power is the antiderivative of 1u to the negative 1/2. But then I have to write a plus c because it's possible that there could have been a constant here. Even if the constant were 0, it's possible that it could have been here in the antiderivative, because then when you take the derivative of that constant, it would equal 0. So it would equal this final derivative. At this point, I can actually substitute in my u again, which was 1 plus x plus 2x squared, and then it's completed. So this is my final answer. 2 times the quantity of 1 plus x plus 2x squared plus c. And that's the entire antiderivative for this original integral. In the next problem I'm going to complete here, it has to do with taking a curve, taking a bounded curve, and then revolving it around an axis. In this case, it's going to be the x-axis. So I'm going to be taking y equals x squared, which is an upward parabola, and x equals 1, which is just a vertical line. That's going to create a bounded region, and then I'm going to be revolving that around the x-axis. So when you take the area of a region that's bounded by 2 different curves, which would be y equals x squared and x equals 1, and you revolve that around an axis, it actually creates a 3D figure, which we could use to describe the volume in pretty much anything in life. We can use that in this example to describe this bounded region being revolved around the x-axis. Here we go. So I'm going to draw that graph very briefly. Okay, so here is the line x equals 1. It's just the vertical line. This is y equals x squared. And then this is y equals 0. We end up having this region right here, which is bounded by all three of those lines. Now we're going to be revolving it around the x-axis, however. So if we revolve it around the x-axis, we end up with a certain kind of figure that has a circular base. So we can actually use the formula pi r squared to describe the area of each one of the disks that this can be subdivided into. You can actually subdivide the figure into an infinite number of disks with increasingly smaller radii to approach this endpoint right here, because this is where all of the lines meet. And then the volume is actually going to be defined by the Riemann sum of these disks being subdivided at increasingly smaller intervals until they're practically touching one another. So when you subdivide the disks at increasingly smaller intervals, then that equals the actual value of the volume of the figure. So we're going to take this area here and then revolve it around the x-axis. We're going to end up realizing that this is at 1 and this is at 0, so our limits of integration will be from 0 to 1. I can write out a of x as the area, and then I'm going to write pi. The upward curve here is x squared. So I'm going to write x squared and then square that quantity. Then I could write this out, but it's really not necessary. I could write this portion here as being the y equals 0. I could actually write that as pi times 0 squared, but it would equal 0, so I won't even bother. So basically you end up with just this area from here to here, and then the limits would be from 0 to 1. So this is the antiderivative that I end up with, the actual integral from 0 to 1, and then pi is on the outside, x to the 4th dx. I can integrate that, and I'll have 1/5 x to the 5th power times pi, and with the limits being 1 and 0. So from here, I can actually plug in 1 into x, and then that would actually describe the volume of this particular figure being revolved around the x-axis. So this is the endpoint. We end up having a value of pi over 5. This is the value for the volume from this figure, and it again was just by taking the Riemann sum of the subdivided disks from this figure at increasingly smaller intervals until they approximated this value. It's defined, that Riemann sum as the limit approaches infinity actually equals this integral from 0 to 1. So that comprises the list of problems that I have for you. My name is Francesca again, and I'm a full-time tutor. This has been my profession for several years now. I tutor calculus as well as most other levels of math, including geometry, trigonometry, pre-calculus, and actually standardized test math as well, and also some other kinds of math for more specific kinds of testing, like an electronics exam is something that I tutored for once before. GRE math is something that I can also do quite well. My education includes high school, of course, and then going to UC Berkeley for 4.5 years. I graduated in 2004, so it was pretty recent, and although my major was in psychology, I actually spent the first 1.5 years as pre-medical, so that's where I got a large, substantial math background. I tutored a little bit during that time, and I actually took 2 levels of calculus, Calculus 1, Calculus 2, during those years, as well as 3 semesters of chemistry. So I acquired a broad range of calculus and chemistry knowledge there. As for my contact information, if you're interested in discussing tutoring at greater length, you can call me. My phone number is 510-689-7654. My email address is info, like information, @learningexperience.us, like United States. And you can actually also take a look at my website, which is www.learningexperience.us, like United States once again. And once again, also you can take a look at iSchools for more upcoming videos on different topics that I'm tutoring, including math, chemistry, standardized tests, paper editing, and anything else that you think that I would be able to tutor you for. Okay, bye-bye.